So 3H, two graphs that have asymptotes. The section today is going to be somewhat, well, there's parts in it that you've seen before. For instance, the exponentials, and I think we maybe touched very briefly. Wow, thank you for coming in and just interrupting my class. It's on the record now. No, I haven't finished marking the tests. I'm about halfway through. All right. Well, there was only 4 of them, and yeah, you know, you've done so badly that it's just easily just cross. No, not quite. Okay. Yeah, so we're looking at exponential graphs and rectangular hyperbolas. The rectangular hyperbolas sounds horrific, but that's really just these things. Oops, not quite like that, but something like that. That go like that. And there's a good reason that they behave that way, which we'll go through. They're grouped together because both of the types of graphs have asymptotes, which we'll talk about in this section. So firstly, sorry, any questions? Yep. And all of the forms of, yeah. Yeah, correct. Okay, so exponential functions first. So we talked about those last year. You've been somewhat familiar with the transformations of exponentials. It was, you know, if you had some number to the power of, you know, x minus h, then that h value determined whether it was left to right, I think. And then if you added a number on the end of it, that would lift the thing up or drop it down, the whole function. And it kind of just influenced the y-intercept. Anyway, so if we take, for example, y equals 2 to the power of x, then as we look through our x powers, you can see the corresponding y values that result there. So if we look at 2 to the power of -4, well, 2 to the -4 is the same as saying 1 on 2 to the 4, which is 1 on 16. It's a very small number, a fraction. And you can see here, as if we go to kind of, you know, negative, very large negative numbers for x, then my y value is just going to get very, very, very small. It's going to approach 0, but never get there. And we're going to start looking at limits and what those mean. So for very small negative numbers here, sorry, very large negative numbers here, our y value tends towards closer and closer to 0. If you have a look on the graph, you can see, oh yeah, it comes down here. It's going to get very close and approach the line, but never quite get there. Because, you know, for any negative number you can give one that's bigger. I say bigger in inverted commas there, than it, or smaller than it. It's kind of bigger, smaller is a tough one there, but it's less than it. So, you know, as you tend towards negative infinity, y tends towards 0, because it tends towards 1 divided by a very large number, which ends up being very, very close to 0. So the 3 key features shown in sketching these graphs. So the y-intercept is at y equals 1, always, in something of this form. That only changes if we add or subtract a constant on the end of the function. Reason being, because any number here, so we replace 2 with whatever number it is, and to the power of 0, which is, you know, right at that y-axis when x equals 0, and as long as it's not 0, but then the function doesn't exist, it's going to equal 1. So that's why our y-intercept equals 1 there. So just think about, you know, 2 to the power of 0, well, anything to the power of 0 except 0 is 1, and so we get that result. When x equals 1, over here, y equals 2, obviously because 2 to the power of 1 is 2. So whatever your constant is, in this case we had, you know, 2 to the power of x, but a to the power of x. So if y equals a to the power of x, then when x equals 1, y equals a. Josh? Sorry? Yep. Then it turns it into a fraction, remember? Yeah. Yeah. So, you know, like as I said, like, well, 2 to the power of -2 is the same as saying 1 on 2 squared. Remember, so the whole term drops below, and then the power becomes positive, and that's 1 on 4. So if we input -2, our output is a quarter, or 1 on 4. 0.25, as you seem to like using decimals instead of fractions. You atrocious individual. Okay, so yeah, they're fine. It's annoying on graphs. Okay, and then the x-axis is horizontal. Is the horizontal asymptote, as we talked about below. Unless we add a constant onto the end of the function, then whatever that constant is, it's 1 plus that constant. Yep. Limits and asymptotes of exponential functions. So, like I said before, on the far left, as x becomes a very large negative number, then the result becomes very small, because 1 divided by an extremely large number is an extremely small number. And as we approach infinity, yeah, we have that. I would write something like that part down. So the green highlighted part, there's not a lot of notes in this section. A lot of it is just me explaining things. But the highlighted parts are things that are worth writing down. We've seen in the essential class, we've seen before this sort of terminology, but we haven't really used the terminology to the right of that. Sorry, when I say this sort of terminology, I mean this, but we haven't really used this so much. And that's what we're going to start heading towards, and it's usually useful. Sometimes it doesn't give us as much information as we want, like if we are approaching 0 from left or right, from the positive or the negative, then we can use different terminology there. There's a small mistake in the textbook which they haven't got back to me on, but I'm relatively certain, like I'm really certain that it's a mistake. Because clearly here, if we have as x approaches negative infinity, y approaches 0. So then the limit as x approaches must be negative infinity, can't be positive infinity. Y approaches 0. What happens as, on this graph, if we're looking here, what happens as x approaches positive infinity? Y goes to positive infinity as well, yeah. So there's no limit on the right side, only on the left. Like there's no asymptote, there's no vertical asymptote there. It just keeps going to the right, and the graph keeps going up. All of those things. Okay. I'll just read through that. So if we can make y as small as we like by choosing a sufficiently negative x. We can make y as large as we like by choosing a sufficiently large positive x. So that's all that happens. There are no negative values. So there, let's talk about that. So as x approaches negative infinity, what does that look like on the graph? When we say as x, we're talking about our horizontal axis here. And as our values on this horizontal axis start going way far in this direction to negative infinity, then our y value, our vertical, like where the line is on the vertical axis, starts getting very close to 0 until you can't really tell. Question? No? Okay. That's all. So yeah, write this part out as well. The as x approaches negative infinity, y approaches 0. So that's the terminology when you see an arrow like that in this form. It's just saying as x approaches or tends towards, either way. And then the limit notation here, just put a negative in front of that infinity, as I've written out there. That should be there. I've sent through so many corrections now that they've given me a direct email to the person that's doing the corrections. They're like, oh, thanks so much. Please keep sending them through. So I think anyway. Well, look, I mean, as you guys are well aware, I do make mistakes as well. And when you're writing a textbook, it'd be pretty hard to, edit, publish it first go without making any errors. I don't think I could do that. Sorry? Yeah, well, it's just, that'd be lovely. Alas, well, a couple of dollars wouldn't do much. I don't find that many mistakes, but there's a few. But yeah, the reason being is the textbook is quite new, given that the syllabus only came out for last year. So this year is the first time that the new syllabus is being done as HSC, which is why we kind of don't have any. Next year we'll have past exams, literally one past exam for the year 12. So it's just like everyone, yeah, but everyone will be in the same boat. No, a lot of the content is the same, so we'll be able to go through and have a look at which one those things are, but some of it will be different. Okay, so in this particular case of this exponential, Josh, do you want to share it with the rest of us? You can always take it to Nessa. Take it to the board. Yeah, I don't think so. I don't think so because it scales because everyone is in the same boat. And remember, it's a ranking system. Your ATAR is not being compared with previous years. It's being compared with everyone in the same this year or next year. Yeah. Doesn't matter. Your ranking is on your year. Yeah. Yeah, it does. Yeah. So you're right. Like obviously with the terrible terminology of calling kids dumb and smart, but yes, that's right. The universities have a limited number of placements every year. That being said, someone who if they got an offer or someone that applies, and if their ranking, for that year was significantly higher, then I think, they would be like quite eligible, more eligible. The reality is it just doesn't work out like that. Like every year is pretty much the same. With it can vary slightly, but there's never huge variations. The long-term trend can be a big difference, but so no, yeah, okay. So the x-axis is called the asymptote in this, just by coincidence that it is an asymptote in this situation, and then they're just from the Greek word asymptotes, meaning apt to fall together. Cool. Because the curve gets as close to the x-axis as we like for sufficiently large negative x values. And that's really it. So we'll go over, there'll be, questions on those sort of things, but you have been exposed and the stage 5.3 syllabus is assumed knowledge. So we'll have to assume that you can translate those if we need to. I don't think we're going to be translating them, but who knows? Hopefully not. Anyway, we'll see. So the other type is the rectangular hyperbolas, and these do have two asymptotes for a very good reason. These are interesting in how they behave. So they're called rectangular because it can be, well, I don't know if it's because, but it can be shown in the form of x, y equals 1. As far as the equation y equals 1 on x. Thanks, Josh. Yeah, you turned around talking to Michael half the time. With your eyes. Okay, so y equals 1 on x can also be written as xy equals 1. And then if you think of xy as lengths, like, length and width. Length and width equals 1, area. And these are, we haven't talked about their inverse or direct proportion yet, but we'll talk about that shortly. And rectangular hyperbolas. So there's two disconnected parts called branches, essentially. And if you think about it, like on here, if we start inputting, 0, 1 on 10, 1 on 5, half, 1, 2, 3, 4, 5, they're going to have like opposite proportions here. Obviously, it can't do 0 because 1 over 0 is undefined. 1 over the limit of something approaching 0 is going to be infinity, which makes sense on here. If we have a look where this first chart here is essentially looking at this section of the graph. You're distracting me now. Yeah. Okay. So this part here is looking at this section of the graph. And if we're starting here really close to the y-axis, so very small values of x, that's kind of what they've started with. Well, they started with 0, but then we looked at 1/10. It's pretty close to the y-axis. It's very, like there or something. And so my x value was 10. Sorry, my y value was very high up along that line. And you can see as we get closer and closer to x equals 0, our graph gets further and further towards infinity. and that's the only, so it never really crosses over and touches. By the same token, as soon as you cross over to the other side of the y-axis, then you're down here at a very large negative value for y, and that's kind of what's happened over here, where if we look at, negative 1/10 or negative 1 on 10, our y value is going to be somewhere down here. Yeah. So that's just how they work. They're inverse that way. Now they've left out 0. Where did they leave out 0? No, they didn't. No, they just got very close to it. They didn't put 0 in on this side. They just put it in on the first graph. Yeah. Any questions about that one? Sure. Where's that? Oh, yes. So the limit of y as x approaches, it should be negative infinity, as I stated a number of times. Yeah, equals 0. Yep. Yeah, it is. Yeah, that's it really. It's just describing the function. Well, so because there is no asymptote as x approaches infinity, so we don't have to describe it. Like as x approaches infinity, y approaches infinity, big deal. Who cares? But here, as x approaches negative infinity, y approaches 0. Oh, that's different. Like we're getting a hugely large number here, and we get a very small number here. That's something to note, I guess. And then this is the same thing, but this is more on the right. That's more terminology that we'll use when we are doing equations with that sort of thing. So, yeah, like this is equation terminology. This is more descriptive terminology. Yeah. Okay. Where was I? Okay, so limits and asymptotes of rectangular hyperbolas. So the x-axis is an asymptote to the curve on both sides of the graph. So here, the x-axis, this is the asymptote to this curve. And I know there's it looks like there's 2 curves here, but it's considered 1 curve. Like that, this is the curve, this is the graph. And the x-axis is the asymptote for both sides. We get very close to 0 on the y-axis here, and we get very close to 0 on the y-axis here. It's just that here we're approaching it from the negative side, and here we're approaching it from the positive side, as far as the y-axis goes. So as they've said there, so we can make y, we can make y as small as we like by choosing sufficiently large positive or negative values of x. So if I'm picking negative values or positive values, large negative values and large positive values of x, y is just going to get very small and approaching 0 either way. And then we say as x approaches negative infinity, so as x approaches negative infinity, as we go far in this direction, y approaches the limit 0. The ways they've written that, so you're like as x approaches infinity, y approaches 0, or the limit of y as x approaches infinity of y equals 0, or the limit of y as x approaches infinity equals 0. These mean the same thing, just writing it different ways. And then the other side of the graph, as x approaches negative infinity, y approaches 0, or the limit as x approaches negative infinity of y is equal to 0. Questions? No? Yep. Correct. They're just 2 different situations. This, the one on the left is describing the graph. Of course, pen stops working. Is describing the right side of the graph, and the one on the right is describing the left side of the graph. So they're not necessarily descriptors of the asymptotes. They're descriptors of the function, like as far as describing the nature of the function. Yep. Yep. Yeah. So as x approaches infinity, like over here, that's when x is approaching positive infinity. And you can see y gets very close to 0, like it's on the y-axis. Okay. And then obviously the same in the opposite direction. That's okay. The x-axis is, oh, sorry, the y-axis. So we have two asymptotes here. We have the horizontal asymptote and a vertical asymptote. It's going to be very similar, probably just words going in a slightly different way, but describing the y-asymptote or the nature of the graph as y gets very large in the positive and negative directions. So yeah, the y-axis is the second asymptote in the graph. On the right side of the origin, when x is very small but positive, so as we get very close to here, as x essentially approaches 0, what happens to y? As x approaches 0 from the positive side. Yeah, y tends to infinity. Yeah, yes, yeah. And as we approach, as x approaches 0 from the negative side, y approaches negative infinity. Correct, okay. And that's those two things in a nutshell there. So as x approaches, and here's some terminology that a lot of you won't be familiar with, but we say this means as x approaches 0 with a 0 with a plus on it means 0 from the positive direction, so from the positive side. So specifically we're referring to approaching 0 here from the positive area for when x is positive. Yeah. And then the other one would be approaching 0 from the negative side. So as x approaches 0 from the positive side, y approaches infinity, and as x approaches 0 from the negative side, y approaches negative infinity. Because we are going from here, and then we're going from here, and as you can see, as we get closer and closer to here, our y value gets larger and larger in the negative realm. Okay. Okay, so direct and inverse variation. So these are, essentially just talking about as one thing gets bigger, the other thing gets bigger would be a direct relation. An inverse relation would be the opposite. As one thing gets bigger, the other thing gets smaller, or as one thing gets smaller, the other thing gets bigger. And that's all we're talking about there. So, I don't know, yeah, it says we're introduced in previous years. I don't really remember talking about this before, but nevertheless, as they've said there, so direct variation, a variable y varies directly with a variable x if for y equals kx, k being some constant, some non-zero constant of proportionality. Proportionality meaning that it has a direct relationship. Yeah. So the graph of y as a function of x is thus a line through the origin. Because it's kx. So we use c when it's like separate and it's not directly connected to x. Doesn't matter. It doesn't matter. Yeah, we do run out of letters, and then they go to the Greek and all the other things. But you can call it whatever you want. It's just that it's easier to remember it as k in that case. Okay. Inverse variation is the opposite. So it's going to be y equals k on x, whatever k may be, 1, 2, 3, any number really. It's just that can't be 0, obviously. If it's 0, the whole thing goes to 0. There's no proportionality at all. The graph of y, no proportionality in the sense that if k is equal to 0, then as y increases, x doesn't change, it doesn't go up or down, and so there's no proportionality there. So the graph of y as a function of x is thus a rectangular hyperbola whose asymptotes are the x-axis and the y-axis. That's what we just had a look at before. So inverse variation is also called indirect variation, and the word proportional is often used instead of variation, which is what we're going to be looking at. Applications begin by finding the constant of proportionality. So as they said there, the applications begin by finding the constant of proportionality, which is what we're going to find in this mock example. This may seem like it has nothing to do with what we were just looking at, and it almost doesn't, but it just does, because what we were looking at is just kind of a refresher on how the functions behave. Direct variation. Sorry, what was the sign? Oh, down here is proportionate to. Proportional to. It is. Yeah. So I'm going to do this worked example now. It is. No, it is. It does. Like, is proportionate to. I promise I don't just come up with them myself. It's saying that there's a relationship. Like m is proportionate to x, I guess. No, it's like, well, look, it's more that y is proportionate to x, and then you would define that as y is equal to kx, which would be x. Yeah. No. There's a linear relationship with. Are you talking about? If you're talking about linear equations, then there's like they're not they don't change. The gradient doesn't change in a linear relationship. If you're talking nonlinear, then they change, but they don't really have a relationship like with each other. Sure, it's just fixed. Yeah. Well, gradient is the slope when you're talking about graphs. So I don't know where we're going with this. Yeah. Okay, let's move on. I'll just explain this and it'll make a bit more sense. So the first thing we need to do is essentially define K. So as they've said, garden mulch is sold in bulk with the cost C proportionate or proportional to the volume V in cubic meters. Write this algebraically. So the difference there being they've told us it's proportionate or proportional. And so we know then that this is the case. So the C, the cost, is proportional to the volume. So I can say then in my first statement, C is proportional to V, and that implies that C is equal to KV. So some constant times V. Basically meaning that as K increases, C increases, and vice versa, all those sort of things. Okay. That's essentially it. So we've shown it algebraically. This is part A. I would put a part A there. 23. Sorry. Like example 23. Okay. The shop quotes $270 for 7.5 cubic meters. Find the constant of proportionality and graph the function. So the constant of proportionality is going to be what? What letter? K, yeah, it's just K. So we're going to find K. We're going to plug in two values that we've been made aware of. What's the cost? 270, yeah, so B. So our cost, remember, this cost is equal to KV, and so 270 is equal to K times the volume, which is 7.5. Great. K times 7.5. We will divide, so 270 divided by 7.5. And remember that was dollars divided by 7.5 meters cubed is going to equal something dollars per meters cubed, essentially. Proportionate to? Sure. Well, it's helpful. They do give you values. We're going to... it allows us to then change it into an equation. So if we know that C is proportional to V, then we know that C is equal to some constant times V. Some constant, some integer times V, essentially. Okay, it doesn't have to be an integer, sorry. Some rational whole number? No, it doesn't have. Well, actually, is it? Yeah. Some rational number or irrational number. I'm trying to think of. It's just it can't be the constant divided by the volume. Yeah, is it a real number? Yeah, it's definitely real. I'm just not sure if it's all of the real numbers. Anyway, what do we get here? 270 divided by 7.5? 36. So $36 per cubic meter. So that's essentially the cost. So the constant of proportionality is 36, and then it's essentially $36 per cubic meter is what the cost is. So we want to graph, find the graph of the function. Well, that's fine. It's a linear equation, right? Yeah, it is. And it's essentially going to look something like that. Given that, $0, 0 cubic meters is going to result in $0. You okay? Yep, all good. Anyway, probably should try and actually graph it properly. Okay, so they just are asking. I mean, clearly there are no negative values here because I can't have a negative volume. That's just if I start recording again, it gives us a little countdown. Yeah. So it's a straight line. We've got that line there, that there. Probably should put this across here. This was the 270, and this was how many cubic meters? 7.5. And that, yeah, essentially that's it. And our function here would be C equals 36V. If this is C, and this is V. Yep. 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 Well, it's an application, isn't it?
We're just doing lines and
Sure. Yeah, you can call Y whatever you want, and you can call X whatever you want, really. It's just in this context, this is what we're dealing with. You try to put it in real terms if it's possible. That's all. Okay. So the shop quotes $270. Oh, we've done that. We've done part B. Sorry. Part C. How much does 12 cubic meters cost? Cool. Part C. Well, C is equal to 36V, and we want to know what's the cost of 36 times how many cubic meters? 12. That's it. What is that? C equals 36 is was that 6, 6, and 12? Sorry. 432? Okay. Now, something interesting algebraically, right? This was $36 per cubic meter times 12 cubic meters, right? So it's essentially $36 over m cubed times 12, m cubed. What happens to the m cubes? They cancel out, and we're left with $432. So even units of measure, they work with these rates and all that sort of thing. They can cancel out, and you get whatever the result is. So that's why the pers and whatever that matter. Okay, part D. Well, how much can I buy for $600? So then clearly $600 is equal to $36 per cubic meter times V. So if we divide $600 by dollars per cubic meter, $600 divided by 36 over meters cubed, I'm going to be left with something meters cubed. 67 meters cubed. I'd rather write a fraction. Cool. So yeah, that's essentially that one's done in a nutshell. So that's the direct proportion, not that complicated. Here's where writing out the proportionate thing is going to be helpful. Now, they did a video on this, and I was going to play the video. Was I? No, maybe. I don't know. we can work it out. Here's where you might be like, oh, which one is which? But it actually doesn't matter which way is which. Okay. The wavelength lambda in meters of a musical tone is inversely proportional to its frequency f in vibrations per second. Write this algebraically. I can't remember if it changes with is inversely proportional. I don't think so. With what he's done, you don't have to use that sign. Questions? So we have lambda. Lambda's our new friend. Yeah, we gotta be nice to lambda. Lambda is a letter in the Greek alphabet, that's all. Okay, what was the question? Wavelengths, yeah. Okay, so the wavelength of meters, now they're saying lambda is equal to, essentially, it's inversely proportional to. So I know it's essentially going to be lambda equals k on f, or it could be the other way. We'll actually do it the other way around just to show that it's the same thing. So lambda equals k on f. Why wouldn't it matter even if you wrote f is equal to k on lambda? Yeah, it goes both ways. And you think about it algebraically, if I multiply this up, then I've got lambda f equals k, and I can divide by lambda f equals k on lambda. So you don't have to worry about how you're reading the question essentially. The wavelength, it says it's inversely proportional. Great, it's some constant divided by the other thing. Okay. Okay. Now the frequency of middle C is about 260 vibrations per second. Why have they said s to the -1 there? Yeah, because it's per second. Per is something divided by. Yeah, so that's exactly right. So 260, like saying that per second is like saying 260 over s, and that's like saying 260 times s to the -1. Because if I take a thing from the bottom of a fraction and move it up to the top, then the power becomes negative. Whenever we switch bottom to top, the sign of the power switches. Okay, not that it's super crucial, it's just something that was interesting to note. 260 vibrations per second, and its wavelength is about 1.319 meters. Find the constant of proportionality. Great, so we can find k by getting k on its own. How do we get k on its own? Well, let's just multiply those other two things together. So b, lambda was the wavelength, was 1.319, and that was equal to k on 260. Yep. Now, yeah, either way, it doesn't matter. So 260 times 1.319 gives us what value of k? I agree. I agree. It is slightly bigger. No one else is getting their calculator out. That doesn't sound correct. 342.94. 342.94. And that's our constant. So that is essentially, yeah. Well, if this was meters and this was 260 s -1, yeah, meters per second, yeah. Okay, we done? All right. So we've essentially here got, yes, meters per second. And that's that. We times those two things together. Huh? Oh, any questions about that one? No? Okay. Now find the wavelength of a sound wave with a frequency of 440 of that. Great. Well, we know what our K is. We have K. K equals that. Cool. So part C now. Let's move C up there. Find the wavelength of a sound wave with regards to that. So the wavelength, what was representing our wavelength? Lambda. So lambda is equal to 342.94 divided by 440. And this was meters per second squared divided by 440 per second, vibrations per second. The result there is obviously going to be meters. And what was it? What's it non-rounded? Not everything, but give me a few more digits. 7794. Let's go away. What are you guys giggling about? Okay, let's keep it related. Okay, 7794. They've gone to 779, so we'll leave it there as well. And that was meters. So nearly a meter. Cool, not quite though. B, B, C, D. Find the frequency of a sound wave with wavelength 1 meter. What's that going to be? Work backwards, yeah. So essentially 1 equals 342.94 over frequency. So frequency would have to equal what? 342.94. So the frequency is exactly the same as the vibrations, which makes sense. So what's the approximate speed of sound in air? You could, don't need to. Yeah, it's well, essentially, so it's about 343 meters per second because there's 343 waves, each 1 meter long, go past in 1 second. So if they're 1 meter long, yeah, bit of a physics, but not really. So that's the speed of sound, yeah, about 343 meters per second. So if we can go like 400 meters away from each other, it's going to be just a little bit over a second, and then we could watch. So we could do this at the athletics carnival. We could make something pop, and then we could see it pop, and then see that a second later it would the sound would get to us. It's very exciting. How can you increase the speed of sound? Yeah. You can. This is a terrible question, terribly phrased question. But if you convert the sound into radio waves, then it goes at the speed of light. Yep. Radio waves are light. They're just... Sorry? Yell in the train? Yeah. Oh, that's a good question. Yeah, so is the speed of sound, is that a constant? Is the speed of sound a constant? Depends on the atmosphere, right? Yeah, no, it's a good question. I'm pretty sure it, because if the sound, the air that you're speaking through isn't moving. So if you're just running along, then no, your speed isn't going to change. But if the train's moving along and the atmosphere in the train is moving, then yes, but like the speed that we would detect sound would be relative to the atmosphere that it's in. For example, right now the Earth is traveling around the sun at 100,000 kilometers an hour. And so, so all the sound is moving faster than, than the speed of sound because we're moving around the sun. But yeah, it's got to be relative to the atmosphere that it's in. Okay. Anyway, there's one more thing to go through here. This is literally just explaining about direct and inverse variation, how they're closely related. So if we look at a very simple example of some kind of rectangular object, like a rectangle, then direct and indirect variation can be quite clearly observed. So if we look here, the area is equal to x times y, and the value of y is equal to the area divided by x. And so if we're trying to keep one of them fixed, then the other two things are going to change. So if the side y is a constant, so if this stays the same, then the area is directly proportional to the other side, in the sense that as the area decreases, x decreases. If the area is the constant, this is staying the same, then y is inverse to x. So as y increases, x decreases. As x increases, y would decrease. So let's look at it like this way. I've got area, I've got x, and I've got y. What stayed the same? Let's assume that y has stayed the same here, but x has clearly decreased, and so the area has clearly decreased. Now, if my area is going to stay the same, then much trickier, let's say the area has just stayed the same, y has increased, and therefore x would have to decrease. That's it. It's just the direct, just getting a grasp on that. If you can read that and understand it, that would be helpful. That's all. Yeah, it's a little bit stating the obvious. No, well, that's the thing. These two things are demonstrating that as area increases, is that what we said? No, if area increases, both of these things increase. Or one could increase, yes. Yeah, that's what they've said. Yeah. Doesn't have to be. In the situation when we're talking about proportion, yes, we want to keep ones the same so that we can definitively see what's happening to the other. So yeah, if this is constant, this stays the same, then this is directly proportional to this, because as this increases, this increases. As this decreases, this decreases. And then if this is the same, then as this increases, this decreases, and vice versa. Yeah. If something is proportionate to something else, so like if A is proportionate to B, if it's directly proportionate, then A is equal to some K B. Yeah. And if this stays the same, then they're both going to increase or decrease. Yep. Yep. We have no idea what any of those things are. Yeah. Well, no. If we have A equals K, then they're not proportionate to each other, because like they're just equal. But it's not a relationship. They're just two things being equal to each other.
So if K equals A equals KB, if K equals 1, they're not proportional to each other.
No, they would be. So, okay, we're getting mixed up between constants and variables here. So let's look at like y equals x, directly proportional.
Yeah.
Yeah, because my k is 1 here. Yeah, that's fine. They can be directly proportional. If we're substituting values in, so if I put in a value for 4 for y, well then clearly x is 4 as well, so on and so forth. So yeah, they're directly proportional. If I looked at 1 on x, then they're inversely or indirectly proportional. Well, because I was saying that both of them were constants. Well, even if a is not a constant, if k is a constant, then only one value for a can exist. Yeah. So a would have to be a constant by definition. Okay, Mason. Okay, I'll just finish that's we're done.